Welcome to The Explainer. Today, we're diving into a statistical tool that's a real game changer, one that often separates the good from the truly great in data analysis. If you're in a data-driven role or gearing up for a Six Sigma exam, really understanding the Cox Transformation is, frankly, non-negotiable. So let's kick things off with a situation that, let's be honest, every single one of us in data has faced. You've done all the hard work, you've collected the data, and you're ready to build that killer model. But there's a problem. Your data is just not behaving. It's breaking the rules, and that leads to the critical question. How can you possibly trust your conclusions when your foundational data is flawed? And this really gets to the heart of it. Think about it. Many of our go-to statistical models like linear regression or ANOVA are like high-performance engines, and they have one non-negotiable requirement for fuel. Your data needs to follow a normal distribution, that classic bell curve. If you ignore that and proceed anyway, you're not just risking a slightly off-kilter result. You could be making decisions based on insights that are fundamentally wrong. The entire foundation of your analysis just crumbles. Okay, so here's our plan of attack for this explainer. First, we'll nail down the why, the problem with non-normal data. Then we'll introduce our hero, the Cox solution. We're going to pop the hood and see exactly how its secret sauce, this thing called the lambda parameter, actually works. After that, we'll get practical and walk through an application. And finally, we'll put on our consultant hat to talk about the fine print, the limitations, and the big takeaways you need to know. So let's get really precise about the problem. Why do we, as analysts, care so much about this idea of normality? Let's break it down. You see, when we use models like linear regression, we're leaning on a few core assumptions, and normality is a huge pillar in that foundation. If that pillar is cracked, the whole structure gets wobbly. Your predictions will be less accurate, and even worse, you risk falling into some serious statistical traps, either seeing a significant effect that isn't really there or completely missing a critical insight that is. Normal data helps ensure the relationships you're modeling are genuinely linear and that the variance is stable. Without that, you're building on shaky ground. So what's the move when our real-world data is, well, messy? When it just refuses to play nice and fit into that perfect bell curve? We can't just ignore it and hope for the best, right? Fortunately, there's a really elegant solution. And that solution is a super clever statistical method cooked up by two British statisticians, George Box and Sir David Cox, way back in 1964. The best way to think about it is as a pre-processing step. It's like a data shaping tool. It doesn't change your core information, but it mathematically rescales your data so it looks a lot more like a normal distribution. This allows you to meet those critical assumptions your models demand. Now, this tool doesn't just work on anything. It has some very clear ground rules and some very specific goals. On the requirements side, your data has to be positive. We're talking strictly greater than 0. No negatives, no zeros allowed. And it needs to be continuous. The goals, they're just as clear. Get the data normal, stabilize its variance so it's not all over the place, and improve the linear relationship you're trying to model. All right, now for the fun part. Let's get into the mechanics of how this thing actually works. Its power really comes down to finding the sweet spot for a single, crucial parameter. This is the real secret sauce of the whole operation. That parameter is called lambda. At its core, the Cox transformation is a power transformation. It takes your data and raises it to the power of lambda. The magic, though, is in finding the optimal lambda. The analogy of getting new glasses is perfect here. The software is like an optometrist, flipping through different lenses. Those are the lambda values, usually from -5 to 5, until suddenly your data's distribution snaps into the clearest, most normal focus possible. And this table shows you exactly what those different lenses do mathematically. So for example, if the optimal lambda is 2, you square your data. If it's 0.5, you take the square roots. A lambda of 1 is interesting. It basically means, hey, your data is already normal enough, no transformation needed. And then you've got the special case. A lambda of 0 doesn't mean raised to the power of 0. It means you apply a natural log transformation. So the key takeaway here is that this isn't just about applying some random formula. It's an optimization process. As this quote highlights perfectly, the entire goal is to find that one single best lambda value that reshapes your data into the closest possible version of a normal distribution. Okay, we've got the theory down. Now let's move to execution. How does this actually work in the real world, especially within a structured framework like Six Sigma's DMAIC process? For all you folks working in quality management or process improvement, this isn't some abstract statistical toy. It has a specific home inside the DMAIC process. You'll typically use it in the measure phase, after you've collected your data, but before you can assess process capability, you need to make sure that data is normal. Cox is the tool that gets it ready for that crucial analysis. In practice, using software like Minitab is a pretty straightforward three-step process. Step 1, test your raw data to confirm that it's not normal. Step 2, run the Cox function, let the software find the optimal lambda, and generate your new transformed dataset. And step 3, and this is critical, don't ever skip this, you have to retest the new data to validate that the process actually worked. And this slide is the perfect before and after picture. On the left, you see the original skewed data. That super low p-value confirms what our eyes are telling us. This is not normal. But on the right, after the transformation, the picture is completely different. The histogram now looks like that bell curve we need, and the high p-value confirms our success. We now have statistically valid data to work with. Now, a quick note for anyone studying for an exam. You won't have Minitab in the test, so don't worry about the complex calculations. What's important is that you understand the concept. We transform non-normal data to make it normal. And you should be able to recognize the basic formula, that the new data point is just the original data point raised to the power of lambda. That's it. Okay, let's bring it all home. For this last part, we need to approach this from a strategic consultant's perspective, because any good analyst knows that no tool is a silver bullet. We have to be really clear about the trade-offs and the fine print of the Cox transformation. Yeah, there are several important caveats to keep in mind. We already know it only works for positive, continuous data. But the biggest trade-off from a business perspective is the loss of interpretability. You can build a statistically perfect model, but if you have to explain to your stakeholders that a key driver is the inverse square root of customer call times, you've lost them. You are making a direct trade, gaining statistical validity at the cost of an intuitive explanation. And it's also worth remembering that with huge datasets, this might not even be necessary, as some models are robust enough to handle a little non-normality. So we leave you with this final, critical question. The Cox transformation is an essential tool for ensuring the statistical integrity of your work. It gives you the power to build valid, reliable models. But it also introduces a challenge that every great analyst and consultant has to master: that balance between mathematical rigor and clear, actionable communication. You've normalized the data, but the ultimate test is, can you still explain it in a way that drives smart business decisions?